Okay. Hello, boys. Today, as can boy guess from the title, we will be okay. Yeah, I cannot pull up British accent, but we will be doing the second video of the AP Physics 2 series. And today, I will be covering fluids in motion, and if there's time, maybe even gases and the kinetic theory of gases. But for now, we're just gonna go in the order that I delineated in the previous video. So yeah, and first we're gonna talk about Bernoulli's principle. And Bernoulli's principle states that actually I think it's just a lot easier if I type it out. So it states that the pressure. Okay, that was I don't know why it's capitalized. Uh, okay, that's better. Pressure that a fluid exerts on a surface decreases. Okay, not decreases as the speed of the fluid increases. And yes, that's basically just the gist of Bernoulli's principle. And it actually has a lot of real life applications and examples. Like, for instance, if you have a vein or artery that's clogged with like fat or something, then it's going to slow down the blood. And that's what causes high blood pressure. So, yeah, that's an example of Bernoulli's principle in real life. So yeah, and also has applications with how like clarinet works. And by the way, I think I mentioned this in the previous video, but when I say fluid, a lot of people just tend to associate it with just the liquid, but it's actually refers to either a liquid or a gas. So this is applicable to either one of those. Yeah, I gotta be fancy with the cursive. Anyways, now let's talk about flow rate. So flow rate is just basically the speed at which a fluid moves through some surface or medium. So, for instance, if I had like a cylindrical pipe like that, then the flow rate would just be speed at which some volume of fluid is moving through the pipe. And flow rate is denoted with Q, which is not to be mistaken for heat, because heat also is denoted by Q, and so is charge, but this flow rate is Q in this context. And it's equal to the amount of volume of the liquid over a certain time interval. Or you can also, as t gets smaller, in the limit as t gets smaller, it's just dv dt. And as you can probably guess from the formula, the units are cubic meters per second, or the SI units rather. And yeah. And since in the case of it moving through a pipe, flow rate is the cross-sectional area times the length of the volume that's moving through is equal to the volume. We can rewrite flow rate as so Q. We said it was originally Q is equal to V over delta T, but now let's say that the length of the fluid is delta X. So now it'll just be A delta X over delta T. And if we can see that the the change in position with respect to time, or in other words, dx dt, is the same thing as the speed. So we can also rewrite it as the cross-sectional area times the speed. So yeah, both of these formulas work for flow rate depending on the information that you're given. And yeah. Okay then, so let's do a practice problem. Okay, so this is from the textbook I'm using, but the heart pumps blood at an average flow rate of 80 centimeters cubed per second. So that's Q. and into the aorta, which has a diameter of 1.5 centimeters. But since we don't use diameter, we can say the radius is 0.75 centimeters. Determine the average speed of blood flow in the aorta. Oh, okay, wow. So this is not too bad. So we're assuming that the aorta is cylindrical. In that case, we can use pi r squared for the circular cross section. And we said that Q is equal to AV, but we want to find the average speed. So we can just rewrite this as V is equal to Q over A, which is just Q over pi r squared. And R is just 0.75. And if we plug this in, we get about 45 centimeters per second. So yeah, that's the average speed of the blood, and that is an application of flow rate to real life. So yeah. Okay, so now that we have gone through an example that incorporates flow rate, now we can move on to Bernoulli's continuity equation. And it states that, sorry, okay, actually I'm just gonna double check it just to make sure I didn't get it incorrectly. Okay, so for a pipe, which for an incompressible fluid, in other words, most liquids, the continuity equation, also assuming that the material of the pipe is rigid, so it can't bend. In that case, the continuity equation just states that the flow rate is constant. So for instance, if we had a rigid pipe and an incompressible fluid and pipe somehow got thinner here, then we can, since the cross-sectional area here, we're going to call this cross-sectional area A sub 1 and this is A sub 2. Since this is visibly larger than A sub 2, and since the flow rate can be written like this, we can see that V sub 2 must be greater than V sub 1. And so yeah, that's an application of the continuity equation. And actually there's an example problem here which incorporates it. So blood normally flows an average speed of about 10 centimeters per second. So we'll call this V sub 1 and it's 10 centimeters per second in a large artery with a radius of about 0.30 centimeters. Assume that the radius of a small section of the artery is reduced by 1/2 because of atherosclerosis, a thickening of the arterial walls. Determine the speed of the blood as it passes through the constriction. Point 2 in the figure below. Okay, so we're gonna call this R sub 1. So R sub 2 is half the size, so it's 0.15 centimeters, and this is V sub 1. And here's the thing: I don't actually have to do any calculations because we know that the ratio of the velocities must be the inverse of the ratio of the areas. And since the cross section is circular, the area is pi r squared, so it's proportional to r squared. And so r2 squared is 1/4 of r1 squared. So which means also that a2 is 1/4 of a sub 1, which means that v sub 2 is 4 times v sub 1 in order to satisfy the continuity equation, which means that v sub 2 is 40 centimeters per second. Wait, did I get that right? Yeah, okay, yeah, 40 centimeters per second. And yeah, so that is how you would use continuity equation. Very important to remember. And the continuity equation is not to be mistaken for Bernoulli's equation, which is what I'm about to get to next. and it's a more universal version of the continuity equation because it works for different pressures as well. And yeah, but it's also a little harder to memorize. Okay, so I'm not going to get into all the details of the derivation, but Bernoulli's equation states that if okay, so just as an example, I'm going to draw a pipe, and let's say it tapers over here, and the elevation changes, and we're going to say that over here the liquid flows at V sub 2, and it's at elevation, I'll just call this Y sub 2, and let's say the pressure here is P sub 2, and let's say that liquid has some constant density. And likewise here, the elevation is Y sub 1, and now it's traveling at only V sub 1, the pressure is P sub 1. So then Bernoulli's equation states that P sub 1 minus P sub 2 is equal to 1 half times rho, where rho is the density of the fluid, times V sub 2 squared minus V sub 1 squared, plus rho g Y sub 2 minus Y sub 1. Or, if you want, you can write it as rho g delta y. And personally, I think this is kind of a pain to memorize. Another form that I find easier to memorize because of the symmetry is just 1 half rho v 1 squared plus rho g y sub 1 plus p sub 1 is equal to p sub 2 plus 1 half rho v2 squared plus rho g y sub 2. And this is the one I use. They're both the same thing. You can solve it yourself to see that. But personally, I think that the latter is just easier to memorize. And yeah, so this is known as Bernoulli's equation. And the previous one is the continuity equation, although it's sometimes called Bernoulli's continuity equation, but yeah. And unlike the previous equation, this one's more universal because it also takes into account differences in pressure. But it assumes that density is constant, which is usually the case for like most liquids. And actually, I think we are done. Actually, okay, so next there's viscous fluid flow, but that's not really covered in AP Physics 2, so I'll be skipping that. And yeah, I think we can move on to gases, which I have now. Oh, actually, there's thermodynamics. Actually, yeah, I'll just do gases, and if there's time, maybe we can move on to thermodynamics. Let me just see where gases are in my book. Because gases set a good foundation for thermodynamics. Like some concepts are easier to understand once you're introduced to gases. So yeah. Okay, where is the chapter? Okay, yeah, I found it. So gases are just basically, actually let me erase all this. Oh wait, why am I doing that? Can I just clear it? Okay, that's much better. So gases are basically a bunch of particles moving in space, but they're less dense than liquids. And the molecules can easily go around each other, which is not the case for solids, and it's not as much the case for liquids. And what distinguishes gases from the other phases of matter is that they are easy to compress, while liquids and solids are almost incompressible. In other words, gases have no like fixed volume, and their volume um, they like adjust to occupy the volume of whatever their container is. Okay, so with that being said, it's time to introduce the ideal gas model. And basically, in this context, ideal does not mean perfect. It means simplified. Like it just makes our calculations easier when we use the assumptions that this model entails. So yeah, and in the ideal gas model, first of all, gases or the individual molecules are considered point-like masses, and they only interact with each other in the walls of their container through collisions. And also, the model assumes that the particles and their interactions are accurately described using Newton's laws, and that all collisions between particles are elastic. And this just makes calculations easier. So it isn't in this context. Ideal doesn't mean perfect so much as it just means simplified. And yeah, so next is pressure. And as I mentioned in the static fluids video, pressure is the perpendicular force over the area. And the same is true not just for liquids but for gases. So if you have more gases hitting a given area, then obviously there's going to be more pressure. And this force is simply equal to mass times acceleration, or in other words, mass times the change in velocity of the gas over the time it takes for the collision to occur. And yeah, so that's just the formula for pressure, and yeah, and let's see. Some instrument. Sorry. Okay. So wait. Never mind. That's not covered in physics too. And actually, I don't know why the book's repeating things, but it also mentions density, which I already went over. It's mass over volume, and yes, it's true for both liquids and gases. And obviously, the SI units are kilograms per meters cubed. Okay, finally, we'll be introducing. If you've taken chemistry, you probably already know about this, but we're going to be introducing Avogadro's number and the mole. And basically, the purpose of it is so when you're dealing with problems with gases, obviously we're going to be dealing with several orders of magnitudes of molecules. So it's easier to use moles so that we have like less things to deal with, if that makes sense. And so Avogadro's number is equal to 6.02 times 10 to the 23 of something. And so 6.02 times 10 to the 23 particles is the same as 1 mole. So 1 mole is, well, not just particles, but like 1 mole of anything would be 6.02 times 10 to the power 23 of that thing. And I'm not sure if this was some sort of arbitrary number or if it like was somewhat derived, but yeah. So for instance, 1 mole of lead is 207 grams. And this simply means that 6.02 times 10 to the power 23 lead atoms has a mass of 207 grams. And say that's Avogadro's number. And next is another concept that we'll introduce that you've probably already heard about is temperature. And temperature is actually related to the average kinetic energy of particles, of gas particles, like in a container. Like, so, in other words, if you have some container with gases or particles of gas, the faster they move, the higher the temperature. And yeah, in fact, there is this formula known as the ideal gas law, which states that the pressure of the container times the volume is equal to NKT. So as you can see, it's directly proportional to temperature. So as the temperature increases, and assuming everything else is constant, the pressure should also increase. And yeah, this is known as the ideal gas law. And also, so wait, okay, and so I should actually introduce each of these. So we know that P is the pressure, and V is the volume. Capital N is just the number of moles times Avogadro's number. So in other words, the number of total particles. And this is known, K is known as Boltzmann's constant, and it's equal to 1.38 times 10 to the power of negative 23 joules per degrees Kelvin. And finally, T is just the temperature in Kelvin, obviously, since it has to cancel out with the Boltzmann's constant. And an equivalent form of this is also PV is equal to nRT. So here n is the number of particles, but here n is the number of moles, and this is lowercase, obviously. R is known as the gas constant, and it's equal to 8.31 joules per Kelvin mole. And T is the same thing as it is here. And these two are equivalent. The only difference is for this form, we're multiplying n by Avogadro's number, and here we're multiplying k by Avogadro's number. And so earlier I mentioned that temperature is related to the average kinetic energy, and for a monoatomic gas, this is actually an equation for this is K average, or in other words, the average kinetic energy is equal to 3/2 kT, and this is only for a monoatomic gas. And this isn't covered in this course, but maybe I'll introduce this in my thermodynamics slash statistical mechanics series that I hope to do in the future. But just this thing called the equipartition theorem, and this is actually derived using that theorem, which is beyond the scope of this. But yeah, I'll introduce it eventually. And yeah, so next are processes. So next we're going to be introducing what's known as ISO processes, which are just processes where either T, V, or P are constant. And if T is constant, it's called isothermal. If V is constant, it's called isochoric. And if P is constant, it's called isobaric. And in fact, something that measures pressure is known as a barometer. So that's one way to remember that. And so back to the ideal gas law, we can see then. So I'm going to use PV equals nRT. That assuming everything else is constant, or in other words, for an isochoric process, since these two are constant in a container, we know that for an isochoric process, P is proportional to T. For an isobaric process, V is proportional to T, and for an isothermal process, P is inversely proportional to V. Or you can also write it as V is inversely proportional to P. And yeah, and this is what they would look like graphically. So if you had an isothermal process and y-axis was pressure, x-axis is volume, it would look like this. If it was isobaric, so now this is volume, this is temperature, it would look like this. And if it was isochoric, this is pressure, this is temperature, it would look like this. And yeah. And I don't think this is too important to memorize because you could sort of simply derive it. But yeah. And actually, I think that's pretty much it for the basics of kinetic gas theory. Keep in mind that this is the average kinetic energy of a single gas particle. So if you want to look at, like, so if I have a container and I have a bunch of gas particles, you can actually get a rough estimate of the total thermal energy of the container. In other words, the sum of the individual kinetic energies, and that would just simply be equal to n times 3/2 kT, where n is just the total number of particles. So yeah, and you can rewrite this also as 3/2 nRT. So yeah, that's pretty much it for thermal energy and gases and pressure, and yeah. Okay, so with that being said, I think this is it for this video, and in the next video, I will be discussing thermodynamics. And well, if just time, I'll be doing the entire AP Physics 2 unit of thermodynamics, but I'll at least try to do the first law of thermodynamics. So yeah, I hope this video helped, and yeah.